Welcome to this course on Introduction to Algebraic Geometry and Commutative Algebra. In the last lecture we have seen the prime spectrum of a commutative ring. We have also defined a Zariski topology on that, and we have done little bit basics of this. For example, we have noted formal Hilbert-Stroum's ansatz, and because of the general setting how easy it was to give a proof, and proof is just commutative algebra language converted into geometric language. Now I am going to see today some more properties of the spectrum, some properties, some topological properties I would say. Properties of the spectrum, spec of A, where A is a commutative ring with identity. So, as it is, as usual, A is always our commutative ring with 1 equal to 1A to be precise, and we have defined this spectrum. When I say the word spectrum, one must remember the spectrum which appears in a optics. So, I write that as an example, what is the connection between this spec and that. So, this spec what we have defined is the set of all prime ideals P where P is a prime ideal in A. And remember our notation, this we have denoted by X. So, and on X we have this Zariski topology. So, whenever we see a word spectrum, that is always with the Zariski topology, and our notation is if you have a point small x in X, when we want to switch to algebra you should write Px. Just to remember, we have come back to algebra and we are going to deal with prime ideals, maximal ideals, intersection, sum, etc. and so on. Alright, so first I will want to prove very basic properties. So, what do we know? We know the closed sets. Closed sets are precisely V of an ideal A, or this is also same thing as V of finitely many elements in the ring A, F1 to Fm. And what are the open sets? Open sets are precisely D of A, which are the complements. This is X minus VA. So, in particular when we have a element F in the ring A, as I said last lecture also, I will denote the elements of the ring by F, G, etc. because our model example of a commutative ring with identity element is the polynomial ring over a field, and those elements, the elements of that ring are precisely the polynomials, and we denote polynomials by F, G, etc. Therefore, I adopt the similar notation. So, this is Vf is by definition all those prime ideals then P in spec A such that F belongs to P, but this is same as this is Px, our notation. So, this you can think of same, these are all those points x in X such that f of x is 0. I keep saying f of x, but f of x, remember f of x is the image of, you have A here, you have A mod Px here, this is an integral domain. So, it has a quotient field, that is the kappa x, this is a quotient field of this integral domain and we have an element f here. This is a ring homomorphism. So, the image of f under this ring homomorphism in this quotient field is denoted by f of x, f x. It is f of x, but this is the image of f. So, that is 0. This is equivalent to saying that because this map is injective, if it is f of x is 0 here, that means it is 0 here, but that will mean that it is in p x. So, this means f belongs to p x. Alright. So, what is the complement df? df is precisely all those. Now, I will directly write here x in x such that f of x is non-zero. See, even when we were studying calculus, the usual standard thinking was being non-zero is always an open property. So, therefore, these are the open sets and this is called a basic open set. So, df family df as f in a forms a basis of the Zariski topology. On x. Alright, now these are the basic blocks, like when you study for example calculus on Rn, then the basic open sets are precisely the open balls. So, these df's take the role of the open balls. Alright, now the first one I want to note that this spec A is quasi compact. I will recall what it means. So, that is every open cover, let us call it x, cover of x has a finite subcover. What does that mean? Let us write in symbols. So, this is the meaning in symbols. If ui, I in I are open subsets in X with cover means full X is covered by this ui, means X is a union of these ui's. Such a thing is called an open cover of X. Then there exists a finite subset J of I such that X is a union of uj. So, that means X is covered by finitely many of the uj's. So, such a thing is called quasi compact. Before I go on, I will also explain the word why quasi compact, why this word quasi. Normally, if you see standard books on topology, most of them will say compact, but when usually one says a topological space is compact, one usually assumes that it is Hausdorff. Hausdorff means, so recall that this I am recalling for, I will recall this quickly because we are not going to go too much into this. Recall that a topological space X is called Hausdorff if for every pair of points x and y in X, x not equal to y, there exist open subsets u and v, which u contains x, y is contained in v, with u intersection v is empty. See, if you want to draw a picture, this is x something, there are 2 points here, x and y, x not equal to y. So, you can find a open set around this x and around this y, they do not intersect. Such a thing is called Hausdorff or T2, it is also called T2. There are many properties T0, T1, T2, T3, T3 and half, T4 etc. and they come from, its T is an abbreviation for Trennungs. Trennung, that means a separation, this is a separation. So, this means the 2 points you can separate them by neighborhoods, such a thing is called Hausdorff. But in our case, Zariski topology is almost never Hausdorff. So, let us write an example first, then we will come back to the proof of this. So, example, suppose that A is an integral domain. Then that means the 0 is a prime ideal in A, and this I will write this as 0 only, I will not write the bracket around that. 0 is a prime ideal, this is our x, and I say any two open sets, every open set, note that every open set, open subset u contained in x will contain 0. Why that? What do you have to show that it contains a 0? That means what? Okay, it is an open set U, therefore, it will contain a basic open set. So, there exists F in the ring A such that with df is contained in U. But F cannot be 0. If F is 0, D0 is everybody. So, if you have a proper open set U, then this will contain this, and 0 obviously belong to the basic open set F df, because what does that mean? This means f of 0 should not be 0, or in other words f should not belong to the ideal 0. This is the 0 ideal. This is the 0 ideal. This is the prime ideal because it is an integral domain. Therefore, 0 will always belong there. Therefore, any proper open subset, any open set proper, even if it is equal to x, it will 0 will belong there. So, any open subset will contain a basic open set, and basic open set will always contain the prime ideal 0. That means the point 0 in the topological space will always be there. Therefore, when I take any two non-empty open sets, I should say non-empty open set. If I take any two non-empty open sets U and V, both non-empty open, then the intersection will always be non-empty, because 0 will always belong there, because it belongs to both, therefore 0 will always belong there. So, therefore, there is no chance of separating 2 points at all, because every two non-empty open sets intersects. So, Therefore, this spec A is not Hausdorff. Alright. So, now we want to prove this assertion that they are quasi compact, means every open cover has a finite subcover. So, we are proving that now. So, proof. So, let ui I in I be an open cover of spec A, which I will call it X, and we want to check that finitely many UIs will cover X already. Alright. So, I can assume, we may assume enough to prove that D F I in I which covers X has a finite subcover, because X is a union of UIs. So, every point in X is in some UI, and I will concentrate on a basic neighborhood which contain that point. So, that means X will also be covered by basic open sets DFIs, and therefore, I will replace these UIs by DFIs, but maybe the indexing set will change, and then I want to extract now finite subcover. Okay, what does that mean, that X is the union of DFIs? This means this means now I take the complements. The complement will say that the complement of X is empty set, that will be this intersection will union will become intersection, and the complements of this, that is VFIs. But we have know the arbitrary intersection of these closed sets is precisely the closed set, and closed set of whom? It is precisely V of the ideal generated by these FIs. That this is the property of V we have checked in when we defined this, but this is V0, V1, sorry, V1. V1 is empty and it is V of this. Therefore, we know that this ideal must be a unit ideal. If V of this is empty, that means there is no prime ideal which contains this ideal. In particular, it has to be a unit ideal, because if it was not a unit ideal, it will definitely be contained in a maximal ideal by Krull's theorem, and that will be prime ideal, and therefore V cannot be empty. So, this first of all implies the ideal generated by FIs is a unit ideal. So, one belongs here, therefore, one will belong to this side. So, that will imply I can write 1 as a finite linear combination of FIs. So, I will call it AJFJ. J is in J, where J is a finite subset of I. Finite subset of I, and these coefficients AJ, they are in the ring A. J is in J. But this will mean already that V of summation ideal generated by Fj's, they are finitely many now. AFJ, this is already empty, because 1 belongs there. Again the same argument, this is a unit ideal, therefore it is not contained in any prime ideal, therefore V of that is empty set. But this is again intersection J in J, VFJ, Now again take the complement of this. So therefore complement of empty set is X, and the complement of the intersection will become union over J, and then this VFJ complement will become DFJ. So we have proved that X has, this is a finite cover now. So that is DFJ J in J is a finite subcover of the original cover DFI. So that shows that it is quasi compact. Alright, so we have seen it is quasi compact. Now when also okay, I will come back soon to the spectrum in optics, but before that I will write down few more properties. Okay, the next one, if you like, you call it a proposition. So let A be a Noetherian ring. Then X equal to spec A is a Noetherian topological space. So recall that Noetherian topological space is the one which means that open subsets in X satisfies ACC, or equivalently closed subsets in X satisfies DCC. So that is the definition of Noetherian we have seen last time. Or one can also say every non-empty family of open sets in X has a maximal element, or equivalently every non-empty family of closed sets has a minimal element, because this is because open sets and closed sets are the complements of each other. Also one more property which I want to use in this proof is the following. X is a topological space, so this I will write as a side mark. Note that this is very easy to check. A topological space X is Noetherian if and only if every open subset of X is quasi compact. This will follow almost from a definition, namely the non-empty open subsets satisfies ACC, you can use that. So these I will just say check. Alright. So we want to prove that this X is a Noetherian topological space. So that is precisely what I want to prove, that every open subset is quasi compact. So by the above observation, it is enough to prove that every open subset in X equal to spec A is quasi compact. Alright, so that means what? How does the open subset look like? So start with an open subset. Every open subset will look like U, which will be complement of the closed set, that is look like D of A for some ideal A, for some ideal A in A. So, let this be an open subset, and I want to prove that U is quasi compact, but our ring is Noetherian. So, since A is Noetherian, A is finitely generated. So, that means A is generated by finitely many elements F1 to Fm. And what is dA then? No, then U equal to dA, which is equal to d of this F1 to Fm, but that is union of d of Fj's j in 1 to m. So, which is clearly quasi compact, This is because, so I will write because each df is quasi compact. And why that? Since this df we can identify with spec of A localized at F, and A is Noetherian, therefore this is Noetherian, and just now we have seen earlier that the spec is quasi compact, therefore this is a homeomorphism. So, therefore, it is quasi compact. So, one more thing and then we will take a break. These are the properties of the Zariski topology of the affine for the spectrum. Alright. So, next proposition. Every closed irreducible subset in spec A is of the form V of P, where P is a prime ideal in spec A. So, we have closed. Irreducible means which you cannot break into two proper closed subsets, union of the two proper closed subsets. So, proof. So, now A is arbitrary commutative ring, A is arbitrary commutative ring. So, first of all, start with any look at V of P. First of all, I am proving that if I take P in so let P be a prime ideal in A, which is we are calling it X, then what is VP? VP is all those prime ideals which contain P. So, I say this is precisely the closure of this P, if you like Px, because it contains P and it can this is closed first of all, and once it contains P, it contains Vp. So, this is a closure of X, and we have seen in the last lecture closure of a irreducible subset is again irreducible. Therefore, this is singleton, therefore it is irreducible, therefore Vp is irreducible. So, that proves Vp is irreducible closed subset of X. Okay. Conversely, actually what I am proving is irreducible. So, let me be a little bit more precise. Irreducible closed subsets in this are precisely this. Alright. So, we have proved these are irreducible. Conversely, now I want to prove that every irreducible closed subset there is a prime ideal P and it is of the form EP. So, start with a closed and irreducible. So, let V of A, this is closed, be an irreducible subset. In spec A. But do you remember we have proved that then the ideal has to be, I will prove that this ideal has to be a prime ideal. Now we assume that A is a radical ideal. We may assume A equal to radical of A, because if I replace A by radical A, this V will not change. Now I will prove that A has to be prime ideal. So, it is irreducible subset, therefore V of A has to be non-empty by definition of irreducible, and now I will prove that this proves first of all A is not the whole ring, that is a requirement for A to be prime ideal. So, to prove that it is a prime ideal, so let F and G be two elements in the ring A be such that F times G belongs to A. Then I am looking for proving either F is in A or G is in A. That will prove that A is a prime ideal and that will finish the proof. So, alright. So, look at we have given this. So, look at V of A, but V of A then V of ideal generated by A and F union with ideal generated by A and G. This is, we have checked this earlier also, but this is very easy to check. First of all, the bigger the ideal, smaller the V. Therefore, this is very clear. Both are contained there. Therefore, the union is contained there. So, and now one checks easily that from here, how do you check the equality? Take any point here, take any x here, that x will every element A in F in A, not F, some H in A will vanish at that there. Therefore, this union is the product. So, therefore, this is F times G is contained in A. Therefore, this is very easy to check this inclusion, that you use the fact that F times G is in this. But these are both are closed and this is union, and therefore, one concludes from here that V of A, because it is irreducible, V of A is either equal to V of ideal generated by A and F, or V of A equal to V of ideal generated by A and G. But if V's are equal, then, but what does this mean? This will mean that when I take the ideal on both sides, this is a, by Null-Chandras it will be the ideal A itself, because A is a radical ideal, and this will contain a power of G, and therefore, so from here you conclude that G will either F belongs to A or G belongs to A. I will simply write use use formal HNS, because it okay fine, I do not say much, that will follow from that, and therefore we have proved that irreducible closed subsets in a spectrum are precisely V of P. And now I will we will have a break, and after the break we will study some examples which are illuminating. So, that will give us some more understanding about the spectrum. Okay. So, thank you, we will meet after the break.